Hello! Welcome to Sensation, some neural principles. The first of these principles will be sensory codes. Sensory obviously refers to vision or hearing, touch, taste, or smell. By code, what do we mean? Well, let's start out with the definition. We can define a code as a set of rules that provide information. And we can further provide information as the reduction of uncertainty. Let's take an example. Let's say that you've got an upcoming test and the professor provides some information about that test. The professor has then reduced some uncertainty about that test. Then let's say that you or another student asks a question of the professor about that test to further reduce the uncertainty. We're getting more information, we're further reducing the uncertainty. With these definitions, we can go on to more fully understand a sensory code as a set of rules that provide information or reduce uncertainty about the environment via detectors or sensors. There are many possible sensory codes. We'll consider two. The first of these is called a rate code, defined as a sensory rule by which stronger stimuli generate more action potentials per unit time. As an example, we can think of strong stimuli, for example, a comparatively louder voice or a comparatively brighter light, as generating a higher firing rate than with their less intense counterparts. The stronger the stimulus, the greater the firing rate. This would be a rate code. And we can contrast the idea of a rate code with the so-called time code, a sensory rule by which stimuli generate unique patterns of rhythms or action potentials. Here, a picture will help us to understand the distinction between a rate code and a time code. In this diagram, we have time along this axis, the x-axis, and we're looking specifically at 1 second of time. The small blue dots that you see across this 1 second indicate the firing of an individual neuron, neuronal spiking. The more dots, the more firing. You can imagine that this might have been the response of a neuron to a relatively loud sound, as one example. If we had a softer sound, and had we been using a rate code, we would have fewer action potentials here. Rather than having 500, we might have only 250. If we had an even softer sound, the firing rate would be lower, and we might have only 100 or just 10 neuronal spikes across this 1 second period. We can contrast the rate code with a time code. And the time code is well characterized by this bottom diagram. Here again, we're still moving across 1 second, but what you might notice is that we have peaks and troughs across this 1 second, and we have about 10 such peaks and troughs. These correspond to the peaks and troughs of the firing rate that we saw above. That is to say that across this 1 second interval, we might have had 500 spikes, but they weren't evenly distributed in time. Instead, there was something of a rhythm. At the very beginning of this interval, we had a relatively high firing rate, as you see here by this spike. And then a few tens of milliseconds after that, we had a much lower firing rate, as shown by this trough. And then the firing rate picks up again over here, and that corresponds to this peak, and then we have a trough. So this combination of peaks and troughs helps us to understand that these spikes are occurring very non-randomly in time. They're occurring in batches that might be spaced on something like an interval of every 100 milliseconds, as one example. But it could have been the case that the spikes were distributed differently in time than what we see here. For example, there might have been a relatively long period of 500 milliseconds where there was a tremendous amount of spiking, very dense blue dots over here. And then there might be another 500 millisecond interval where we see very sparse blue dots, that is, a relatively lower firing rate. So we can think about the total firing rate, or we can think about how that rate may have been distributed across time. And this helps us to understand the distinction between a rate code and a time code. Let's now move on to the idea of sensory adaptation. And we can build on the notion of a rate code when we're understanding sensory adaptation. First, a definition. We can define sensory adaptation, which by the way is synonymous with neural adaptation, as the reduction in the nervous system's response to a repeated stimulus. So when I first introduce a stimulus, I'm going to get a certain rate of firing from my neuron. If I repeatedly show that stimulus to the same neuron, over time, the nervous system will become less responsive to that particular stimulus, and the overall firing rate will be reduced. Sensory adaptation experiments often generate very interesting psychological after effects. We'll take an example, and then you might think of generating some of your own examples. But to get us started, let's take the simple case of thermal stimuli, such as warm or hot water. At time 1 in this little experiment of sensory adaptation, we can have a participant place his or her hand in room temperature water, and obviously the water will feel like it's room temperature. Now, why is that the case? To understand why it feels like room temperature, let's understand that we might have some neurons that are, if you will, tuned to relatively hot water. Other neurons are tuned to relatively cold water. So if we give the participant room temperature water, we are now going to get some moderate levels of firing from the hot-tuned neurons and some moderate levels of firing from the cold-tuned neurons, and that combination will generate the psychological experience of room temperature water. Not too hot, not too cold, some intermediate combination of hot and cold neuron firing. That's time 1. Let's now go on to time 2, where we introduce the adaptation manipulation. At time 2, we might ask our participant to place his or her hand in hot water. And we have them hold their hand in hot water for maybe a minute or so. Now this is a repeated exposure to the stimulus of hot water, so during this interval of time, the hot-tuned neurons are going to be firing at a much higher level than will the cold-tuned neurons. But after repeated exposure to this hot water, the hot-tuned neurons will begin to reduce their firing rate as evidence of sensory adaptation. Now, we're up to time 3, and we return to our initial room temperature water. We have our participant place his or her hand in room temperature water, and all of a sudden now, that water feels cold, not room temperature. Why? Well, it's because through sensory adaptation, we've reduced the relative contribution in the total firing rate that is coming from the hot-tuned neurons. They've been made less responsive through repeated stimulation. So now, relatively speaking, the cold-tuned neurons are going to be firing more than their hot-tuned neuron counterparts. And as a result, you're going to experience the water psychologically as if it's cold, indeed colder than it was initially. And this is the idea of a sensory adaptation experiment and the idea of an after effect. Now that we've understood how neurons have different tuning properties, we can introduce another neural principle. This is the neural principle of a receptive field. We can say that sensory neurons have receptive fields, the range of stimuli to which the neuron responds. So going back to our earlier example, we had some thermal neurons. Some were hot-tuned, some were cold-tuned. These are firing to different ranges of temperatures. That's the range of stimuli to which a given neuron might respond. But that's a thermal example. We can go on to the auditory system. There might be some neurons that respond to relatively high pitches, like those you would hear from a flute. Other neurons might be responding instead to a different range of stimuli, maybe to lower tones, such as those you would get from a tuba. And we could go on and on to different kinds of sensory systems. As one other example, some neurons in your occipital lobe, which we know is specialized for vision, some of these occipital neurons respond to the center of your retina. That's the proximal stimulus that they're responding to. Other neurons in your occipital lobe might respond only to either the nasal retina or the temporal retina. Nasal retina would be the portion of your retina near your nose. The temporal retina would be that portion of the retina nearer to your ear. So we have different ranges of stimulation to which a particular cell is responding. That's the neuron's receptive field. Given that we have these different neural receptive fields, we come to a related but distinct neural principle called lateral inhibition. And we can define this as the ability of an active neuron to reduce the firing rates of neighboring neurons. So neighboring neurons begin to interact. Sometimes they excite each other, sometimes they inhibit each other. And when they're inhibiting each other, and especially when they're inhibiting their nearby neighbor, or they're inhibiting laterally, we have lateral inhibition. Let's take a specific type of lateral inhibition called center surround antagonism. This is a form of lateral inhibition in which concentric regions of a receptive field have competitive interactions. So we're going to be thinking not so much about just left versus right, a lateral inhibition, but we'll think of concentric circles and how the inside might be inhibitory with respect to the outside, and so forth. Some examples would include on-center cells and off-center cells. Let's take a look at some examples. There's something called an on-center ganglion cell, and just to remind you, we can take a schematic of a simple neuron here, and we've seen this before. Here we have the soma, and out of the soma come various processes. We call these dendrites up here. Here's the cell's nucleus. There's one very long process that extends downward, and that's the axon. This is a schematic of the neuron's anatomy and how it's laid out just physically. We can also get a functional description, that is to say its receptive field properties, and that might look something like this. Notice that this does not look like the neuron. This is, if you will, a picture of the neuron itself over here on the left. This is a description of its receptive field, the range of stimuli to which it responds. And this might be an on-center ganglion cell in the visual system. This neuron will fire many, many action potentials if the region of space it's looking at has a bright center, an on-center, if you will, and the brightness is schematized here by these little plus signs, which suggest that we have a light increment in the center. We can contrast that with the annulus, which has minus signs, and these correspond to light decrements in the surround. So this neuron then, to summarize, would respond maximally. That is, it puts out maximal action potentials to light increments in the center and light decrements in the surround. So what would that stimulus look like? Well, here we see it. We have a light increment in the center and relative darkness in the surround. And here again, just to remind you from the preceding slide, we have a schematic of the cell's receptive field. Here you might notice that we have a really, really strong match between what this cell responds well to and what this stimulus is, a light in the center and a dark in the surround. So this cell would, metaphorically speaking, love this stimulus. That is to say, it would fire many, many action potentials. But then if we give that same cell the opposite light distribution, as we see over here, now we have a dark center and a light surround. This is now a strong mismatch with the cell's receptive field properties. The on-center cells would not respond well to this particular stimulus. However, there's another class of cells called the off-center cells, and they have the complementary receptive field configuration. That is, they respond maximally when there's a light decrement in the center and a light increment in the surround. What would that stimulus look like? Well, we can see here that this cell loves to respond to this stimulus. It's got a dark center, and that matches the negative signs here. It's got a light surround. That matches the positive signs here. So because there's a nice match between this physical stimulus and this cell's receptive field, the range of stimuli to which it is tuned, this cell is going to be putting out many, many action potentials for as long as we present it. And then if we change the stimulus to this, all of a sudden now we have a mismatch, and this cell hates this particular configuration of light, and it stops its firing rate. So these different receptive field properties have very interesting consequences for our psychological experiences. Here's the very famous Hermann grid illusion, which you might have seen before. It's a simple grid, and the interesting fact is that most people report that as they're casually looking at the grid, they notice some gray spots occurring in the intersections. And then they attempt to get further information or reduce the uncertainty about what's going on in the intersection. So they'll fixate, for example, right here. And as they fixate the particular intersection, all of a sudden the gray dot disappears. And while they continue to fixate that intersection, they notice that in the periphery of their vision, they can still see gray dots elsewhere. So they attempt to move their eyes to where they think they saw a gray dot. And anytime you move your eye to a particular intersection, all of a sudden the gray dot disappears there. Well, this psychological effect that we're having is arising because of the center-surround antagonism in ganglion cells within our visual system. An important psychological consequence because of this neurological principle. Thanks for watching.